The Bushveld complex is the world's largest layered mafic ultramafic intrusion in the main natural source of platinum group elements such as platinum, palladium, and rhodium, which are concentrated in thin, laterally continuous reefs like Marinsky Reef, UG2 chromitite, and Platte formed about 2.06 billion years ago by fractional crystallization and sulfide segregation in a giant magma chamber. Geologically, this complex is Paleoproterozoic intrusion and placed into the stable Kapval craton and built by repeated injection of tholeiitic magma, producing a well-defined layered stratigraphy within the Rastenburg layered suite. As you can see in Figure 1, the geologic map of Bushveld complex showing the main limbs, zones, and mines.
So for this slide, this flowchart shows the formation stages of platinum group element ore in the Bushveld Igneous complex from magma emplacement to the preservation of platinum group element rich layers. The volume begins with the injection of large volumes of metal-derived magma into the crust, forming a vast magma chamber. This chamber was long-lived and continuously replenished, allowing prolonged cooling and differentiation. The size and stability of this chamber were critical for the formation of layered mineral deposits observed in the Bushveld complex. As magma accumulated, the chamber remained partially molten for an extended period. This incomplete solidification allowed crystals and melt to coexist, forming what is known as a crystal marsh. This environment was essential for mineral movement and chemical differentiation to occur. So, as cooling continued, early minerals such as chromite, olivine, pyroxene, and sulfides crystallized from the melt. These minerals formed at different temperature and were removed from the melt through fractional crystallization, progressively changing the composition of the remaining magma. With continued cooling, the magma chamber began to subside under its own weight. This promotes the downward movement of semi-solid crystal masses toward the center of the chamber, enhancing internal layering. The crystal mass behave as semi-solid slurry. Due to gravity and chamber subsidence, this slurry slump inward, transporting dense mineral phases downward. This movement played a key role in concentrating heavy mineral phases within specific stratigraphic levels. During slurry movement, hydrodynamic sorting occurred. Dense minerals such as chromite and sulfide droplets settled more efficiently than lighter silicate minerals. This process allowed immiscible sulfide liquid to segregate the platinum group elements from the silicate melt. As a result of hydrodynamic sorting, dense mineral layers accumulated and became concentrated into discrete horizons. These layers evolved into platinum group element-rich chromitite seams where platinum, palladium, and associated elements were strongly enriched. This process ultimately produced laterally continuous stratiform reefs such as the Marinsky Reef, UG2 chromitite, and Platte Reef. The platinum group element mineralization occur mainly as disseminated to intercumulus sulfides including pyrrhotite, palladite, and chalcopyrite that often modified by phases near ultramafic pegmatites. Finally, the platinum group element-rich layers were preserved within the layered ultramafic sequence of the Bushveld complex. Repeated magma injection and slow cooling help maintain the continuity and thickness of this economically important ore horizon. Next, the chromitite layers in the Bushveld complex can be divided into different groups based on their platinum group element content. The earliest layers, known as LG1 to LG4, contain relatively low concentration of platinum and palladium. These layers represent early stages of magma evolution where conditions were not yet ideal for strong platinum group element enrichment. As magma evolution continued, the next group of layers, LG5 to MG2, showed moderate platinum group element concentration. This indicates improved condition for sulfide saturation and more effective platinum group element accumulation. The highest platinum group element concentrations occur in the upper layer, particularly from MG3 to UG2 and UG3. These layers are especially enriched in platinum and palladium and form the main economic target for mining operations today. So overall, there is general upward increase in platinum group element concentration through the stratigraphy, although some local variations occur. This trend reflects the repeated magma injections, continued fractional crystallization, and efficient segregation of sulfide-rich melts. So for the mining method, I'll start with breast mining, which is commonly used in the western and eastern limbs of the Bushveld complex. This method is preferred where the ore reefs are narrow and moderately inclined, typically dipping between 20 and 30 degrees. In breast mining, the panels are developed perpendicular to the reef. Drilling is carried out using parallel blast holes, which improve fragmentation and reduce the need for excessive machine movement. Because the drilling layout is efficient and predictable, this method allows for smoother operation and better productivity. And another advantage of breast mining is improved working condition, as the equipment operates in more controlled and organized manner. This makes it particularly suitable for thin and continuous ore bodies such as Maranskite and UG2 reef. The second method is the board and pillar mining, which is typically used in areas where additional ground support is required or where geological constraints make breast mining less suitable. In this method, pillars of ore are intentionally left behind to support the hanging wall and maintain stability. However, because these pillars restrict equipment movement, drilling efficiency is lower compared to breast mining. Machines must be repositioned more frequently, which reduces overall productivity. An example of this method can be seen at the Amandelbult mine, where studies have shown the fewer blast holes are drilled per shift compared to breast mining operation. This makes both pillar mining less efficient but necessary in areas with challenging ground conditions. So the final method shown here is mechanized mining, which is mainly applied in the northern limb of Bushveld complex, particularly in plate reef. Unlike the narrow reef of the western and eastern limb, the plate reef can reach thickness of up to 30 meters or more. Because of this greater width, larger scale trackless mining equipment can be used. Mechanized mining allows for higher production rates and suitable for bulk mining operation. However, it also requires careful control of dilution and rock stability to ensure safe and efficient extraction.
For this section, importance and application of platinum from Bushveld ores, I will focus on how dominant Bushveld platinum is in the global market and where it is used. First, looking at the first figure on the right, you can see that South Africa, mainly through the Bushveld complex, supplied about 75% of global mined platinum in 2019, where Russia, Zimbabwe, and other countries make up only small slices of the pie. This means Bushveld platinum alone accounts for roughly 70 to 80% of the world's primary platinum, and the bar below shows that the total global supply is still strongly mining driven, with about 76% coming from mines and only around 24% from recycling. This heavy dependence on primary ore highlight why Bushveld platinum is strategically important for the global industries. On the below of first figure, the demand pie chart and regional bar show that the total platinum demand in 2019 was slightly higher than supply and is spread across several key regions, especially China, Europe, North America, and rest of the world. This tells us that many advanced economies rely directly on stable platinum production from the Bushveld complex. Moving on the second figure, the first circle summarizes the main application sectors. Autos are the largest, using 36 to 42% of platinum in catalytic converter and in some fuel cell vehicles, which makes Bushveld platinum crucial for emission control and cleaner transport. Jewelry is the next big use, taking roughly 26 to 35%, mainly in North America and China, where platinum is marketed as premium metal. Industrial application account for around 21 to 26%, including the fertilizer manufacture, hard disk, and medical devices such as pacemaker, while investment demands range from 0 to 15% through exchange-traded fund, bars, and coins. Together, these figures show that platinum from Bushveld ores is not only vital for environmental technologies and industry, but also have strong cultural financial roles in jewelry and investment markets.
The Bushveld complex in South Africa is the world's largest source of platinum group metals. While platinum mining is economically important, it also creates significant environmental and health challenges. One of the major challenges associated with platinum mining in the Bushveld complex is environmental pollution. Large-scale mining activities have led to contamination of surrounding soils, rivers, and sediments with heavy metals. Studies have reported elevated concentration of platinum, nickel, and chromium near mining areas. Research by Diaz Morales and colleagues in 2021 showed that platinum and chromium levels were significantly higher close to mining sites compared to non-mining areas. The Hex River, which serves as the main drainage system of the western Bushveld limb, was identified as one of the most affected areas, showing that contamination can spread beyond the immediate mining zones. In some locations, nickel and chromium concentration were found to be up to 3-fold and 13-fold higher than typical crustal values. This anthropogenic enrichment disrupts local geochemical cycles and can lead to bioaccumulation in aquatic organisms. For example, Ramos et al. In 2020 reported that aquatic microinvertebrates accumulated the highest metal concentration at sites with the most contaminated water. In addition to environmental impacts, platinum mining also poses serious health risks to mine workers. Exposure to dust and metal particles is linked to occupational diseases such as pulmonary tuberculosis, silicosis, and pneumoconiosis. Surface platinum mining generates large amounts of respirable crystalline silica dust, which damages lung tissue and increases the risk of chronic lung diseases. A study by Sepedi and co-workers in 2020 found that 93% of male platinum miners were diagnosed with pneumoconiosis, highlighting the severe occupational health risks faced by workers in the Bushveld complex. To address these challenges, platinum mining in South Africa is regulated under the National Environmental Management Act or NEMA. Under NEMA, mining projects must undergo environmental impact assessments and implement environmental management programs before mining rights are granted. These assessments help identify and mitigate the environmental risks at an early stage. The Department of Mineral Resources and Energy enforces compliance through annual audits, performance monitoring, and financial provisioning. Mining companies are required to set aside funds for site rehabilitation, mine closure, and post-closure management. Amendments to NEMA in 2015 strengthened risk-based closure planning, including long-term monitoring of tailings facilities to prevent heavy metal leaching and acid mine drainage. These are common in sulfide-rich mines. In regards to dust, water, and air management, dust control is a key regulatory requirement aimed at protecting both workers and surrounding communities. Measures include dust suppression at stockpiles, roadways, and transport systems. Progressive rehabilitation is widely used in platinum mines surrounding the Rustenburg area. This involves restabilizing slopes, replacing topsoils, and revegetating disturbed lands with native grasses to reduce dust and erosion. To prevent groundwater contamination, tailing storage facilities use liners, decant systems, and real-time water quality monitoring. Air pollution is also controlled through enclosed conveyor systems and sulfur dioxide emissions limits at smelters.
To summarize, the Bushveld complex in South Africa is the world's main natural source of platinum group elements, where layered mafic ultramafic geology and stratiform reef like Marine Sky, UG2, and Platreef control platinum ore formation and concentration. These reefs are mined using underground and mechanized methods and processed through comminution, flotation, smelting, converting, and hydrometallurgical refining to produce high-purity platinum and other platinum group metals for key industrial, environmental, technological, and medical applications. At the same time, serious environmental pollution and health impacts demand strict regulation, environmental management, dust control, and long-term rehabilitation to keep Bushveld platinum production sustainable for ecosystems and communities.